Before lunch, we had ended just before talking about why gravity would be attractive only in this model. I guess it can be implied already why it would drop like 1 over r squared, because remember what we're describing is these Fibonacci chain centerline beams that are running in line with the direction of propagation of the empire wave. So, and we talked about how you can have a very large set of directions in a large quasi-crystal, right? So the larger it is, the more powers of phi that you can go up to for different Fibonacci chains that you can find from the rotational center. So with a universe that's very large, there would be a lot of different directions that particles can propagate. That is, that the dipoles of these empire waves can be in. So if you take a body like the Earth and you imagine you have n fermions or n clock-based particles, then you could say, well, you may very well have about n different directions. Like there's that much degrees of freedom for directions because in part because every one of them is going probably at a slightly different d over t, right? And each d over t is a different power of phi. So there's just be a large set of directions. And so in other words, at a frozen, well, again, it's hard to think about this. You shouldn't fall in the trap of thinking about frozen states, because at that point, any frozen state, there are no particles anywhere. There's no curvature of space-time. There are no ruled surfaces. There's nothing except for just a single location of where you've placed your center emperor in the inflation action on the possibility space. So, so anyway, these beams, though, they would average out to 1 over r squared. Like even if they're not all pointing out from the center and going in line, they're going at all these directions. And when you sum and average it all up, you would have the probability of encountering a beam be more and more probable as you get closer and closer to the Earth, where all of these beams are radiating out in all directions. So that would be that should average to a 1 over r squared drop-off of the strength of that field of those centerline beams coming out from all of the fermions or clocks. So that's more reasonable than what I'm about to tell you. So what if the beam itself has something to do with helicity? Like, what if the beam itself is kind of like magnetic polarity, where matching it A to A would create repulsion, but matching it B to B would create attraction? Okay, so if that's the case, then if I've got all these beams coming out from the Earth, right, and they're coming out in all these different directions, right, only a few are coming out radially, but most are semi-radial, right? Most are coming out at different angles, but they're all coming out and they're dropping on average like 1 over r squared, and 50% of these sign values would be, let us call, plus, and 50% would be negative, because the idea is that there's a difference between the two sides of the dipole of this object, and how two of those dipoles come in contact. If they could come in line with one another, then in line one way, you'd have to force them, because the random walk gearing would be bad, if we can keep using that word, and they would want to get away from each other. But the fastest way to get away from each other is not necessarily just only to repel away, it's to rotate away, to rotate the bad gearing of a plus or a south-south dipole. But on the other hand, if it's a south-north relationship or a plus-minus relationship, then and that's at time 2, then at time 3, the probability of getting out of alignment is low. So with the repulsive relationship, the probability of dipole rotation is high, and with an inline attractive relationship, the probability of dipole rotation is low. And so if I've got this particle out here that has the plus here, I mean the minus there and the plus here, right? It may be confusing because I keep switching back and forth between the label polarity, north-south, and now I'm using plus-minus. I don't want to be too committal. I just want to suggest that we've got what seem to be 3 binary sign values that we may discover in the QSN. And we happen to have 3 very fundamental binary sign values that physics uses: polarity, charge, spin. I don't know if any of our 3 are supposed to be any of those 3, and I'm not sure which is which. But I have a feeling that helicity is charge. And I have a feeling that spin has something to do with this idea of the right-left of the actual gravitational value of 15.5 plus or minus. All right, anyway, so I got this mass out here, okay? It's just a single clock. It's a single fermion dipole particle. And as it's out here far from Earth, the probability in a given Planck moment or frame that it's going to be close to one of these dipole beams coming out from Earth that's going to make any meaningful difference for it relative to its constantly competing self-interaction. So the self-interaction really is a deep part of why I think repulsion even exists. So if we try to base everything on savings, okay, then where it's not going to get more savings and it's going to interfere with its own self-interaction savings, then it needs to rotate dipoles and get away, propagate and rotate to get out of that non-constructive situation that's harming its own potential for electron self-interaction. Okay, so anyway, let's bring this thing closer. So we bring this closer to this big gravitational body. And now at this point, we've got higher probabilities that it's going to make close contact with some random empire ray coming down the center axis of the helix. And let's say that beam is like this, right? So we got this Fibonacci chain beam here of objects that can serve as savings or free lunch. And then we've got this axis of this one's dipole that is like this, right? So it's fairly close to this angle. It's not in line, it's not 180 degrees, but it's close. Now, if it's close and this value here is plus and this value here is minus, again, it may not be as simple as a Fibonacci chain of dimension of points. It could be a Fibonacci chain of 4 groups that are right or left. So I'm not using right or left. I'm not using north or south. I'm just kind of using plus minus, but I don't mean necessarily charge when I say this, plus minus. It's just 2 values. So if it's these 2 values, let's say that then the probability for it to rotate in line is high, because by rotating in line, it can lock into the relative orientations that make its optimal saving section between the 2 greater than what the optimal saving section would have been if they were not rotated in line. Okay, so then we say in our S-index column here, there's a probability for it doing this, rotating this way, that has some S value, and there's this other probability for it not doing that, doing something else. So each of these probabilities is related to how much savings is in the what we call the optimal saving section for that relationship. So in other words, there's an optimal saving section for this relationship, there's an optimal saving section for this relationship, there's an optimal saving section if this moves here, and so on. But not all optimal saving sections for a given relationship are the same S value. So the optimal saving section value is the value of S in each square, each box of the column that represents all of the possible random walk evolutions, where random walk is not just a walk, it could be a spin change, it could be a dipole rotation, it could be any kind of evolution of the quasi-particle pattern. Okay, so now what if this was opposite? What if this were if this has this high probability to become in line, now this one is moving, its vector is moving this way. Okay? That means the savings, the free lunch that it's looking for in the future is along this axis, this helix. So what happens after that is the probability for it to accelerate forward is great. But that form of acceleration is very different than the acceleration we're going to talk about later when we talk about momentum, mass, and inertia. This acceleration is acceleration because it's being paid object savings that are compensating for the lost object savings that are occurring because this accelerates. I'm putting the cart before the horse for some viewers of the video, but most of you in the room understand that why, when we accelerate, we may have a temporary dip in object savings that we can interpret as inertia. Still a conjecture, still being worked on, but been talking with Fong a lot about it, and we share a lot of the same speculations that there is a period of frames when it changes its pitch. That is, it changes its ratio of propagation through space versus internal time. After that change, there will be a period of frames where the S value dips down lower to even what it was, before the acceleration, before it gets to a greater S value. I mean, greater S value is not necessarily good or bad, because with less S value, you can have your particle experience more space, see more of the universe. But with less propagation through space, it can experience more action locally, that is, more time. So it's not that one is better than the other, but when there's a change to it, okay, our game will not let it spontaneously go to a better S value. That is, it won't allow us to spontaneously decrease the pitch, because in the S-index columns, you'll find that column after column, there's a sequence of columns where the S value would go down temporarily during the transition, even lower than the S value that it was. And so the statistics of the game won't pick, the random number generator won't, if it has to pick those columns, it's not going to have high probability on the ones to change pitch, because that would involve a period of very bad savings during the inertial period. We're gonna go over it as a separate section, but it's a little bit necessary to foretell of it, or review it for you, because here, when this had the high probability to rotate inline because of the matching of the positive-negative values here, which again, positive-negative is not charge here, then at time 2 and 3 and 4, it's going to be accelerating in line here. It's going to be jumping forward without inertia, because the savings is being fed to it from this free lunch here. So even though it's losing some of its contribution from its old power of phi, because the idea of momentum is that you get contributions from the past that are contributing to your present. And so one power of phi, that is 1 d over t, or one pitch, we suspect does not share object savings as efficiently as if it's on the same with another. In other words, a power of phi 2 and a power of phi 3 don't share with as much correspondence as a power of phi 2 with a power of phi 2. I'm sure there's still blurriness there. All right, if this was plus plus, okay, if this was plus plus, then the probability of this close angle locking in to be inline would be low. And the probability in the box for that probability random walk would be low. The probability for it rotating instantly out of the way to an angle that is not at the peak of bad gearing, right? In other words, the closer it gets to 180 degrees, the worse and worse the gearing becomes between the two objects. That is, the worse the S value. So this will want to rotate like to at least 90 degrees, and from there it may try to even flip. I mean, that's what magnets do. Throw 100 little magnets with 100 different dipole directions as they're rotating in the air, and as they hit the ground, they'll start snapping in to rotating themselves north, south, south, and they'll join up in one big line. And so so right here we've had this idea of repulsion, right? So it can move away. It'll have high probabilities for random walks moving in these directions, right? And it'll have high probabilities at the same time to be having random walks that also include a rotational component of the dipole. So you can interpret that as repulsion. And then you'd say, all right, then why isn't repulsion and attraction both showing up in gravity? So I've had this one Planck moment, random walk, of this repulsion, right? And in the other case, before that, I had this one Planck moment of attraction. Let's call those the events that happened at a time 2, where we're talking very short durations, like Planck level time domain. In the first case, where we had a time 2 attraction, kind of accelerating down this Fibonacci chain from this beam, then at time 3, what do we have going on? We have at time 3 a very high probability, right, that it's going to keep going down. But there's going to be perturbances. We will find that we're probably going to have something later that shows up that is very similar to a kind of Dirac sea, a kind of chaotic noise in the background, because when we start really deeply understanding what the n-body, large n-body problem of the universe is, or any local system where you're trying to take care of all of the particles by strategically moving around one center emperor at a time, you know, you'd have to even think about that, you'd have to have something like 10 to the 44 frames per second in order to have one center emperor take care of every pattern in the whole universe. And you'd also have to have this magic of empires and savings, so that positions for particles, 99.9999% of the structure of the empire is not the center emperor, is everything else, and everything else can contribute to particle positions. You know, very hard problem to compute, I can imagine. So we're going to have to understand some deep averages or some deep mathematical insights about it. But this is what I want to do. I want to start with a two-body problem and say, come on guys, we can move a center emperor around very fast to model two particles. Think about it. You got 10 to the 44 frames per second in nature. And you could do that. You could totally make that work for me, because I can only comprehend it to about 24 frames per second. How about 3? You'd say, no problem, right? And then if I say, well, how about all the particles in the whole universe? You'd say, okay, well, in principle, yes, but you'd have to have a really, really fast frame rate. And you'd have to have these empires doing most of the work to fill positions of 4 groups for other particles in the universe. So, okay, so because of that noise, this thing at time 3 is going to have some probability of being accelerated off path. So even though it has a high probability to keep chunking down this inline relationship, it also has other squares in the S-index that relate to the noise that happens, because there's going to have to be chaos and order in our model. I mean, there's going to be some kind of correspondences to fractal theory, where fractal theory makes contact with chaos theory and the notion of order and disorder and the beautiful fluidic interactions between order and disorder, like strange attractors. So, you know, that gravitate order from a kernel of order and begin, you know, reducing entropy of a system. So the noise will give you a probability that it will be brought offline. The S indices are statistical, so the random number generator in our simulations will pick them. So there was always going to be probabilities that this is going to go off this chunking path. But if it goes off path at time 5, let's say it stays on path with the probabilities at time 3, time 4, time 5, but then at time 6, one of the S-index boxes, because of just the right fluctuation in this background noise that I'm telling you we will see, plus just the chance of getting a low S value, it goes off. But now, because it's approached the massive body closer, you have to think about the 1 over r squared. So now to match up, to mate up with another close angled beam coming out, it actually has a higher probability after those 6 steps in the direction of the gravitational attractor to enter into a close relationship where the dipole will have a high probability to rotate in line, okay? So there will be more and more increasing opportunities to get in line and then stay in line for several steps, because those are always going to be high probability, then get knocked off by another quantum fluctuation of the background noise. But in the case of the repulsive relationships, they tend to move things further away from the gravitational attractor in those random walks. So they get to a place where there's a little bit less probability of either a positive or negative, you know, a constructive or destructive alignment. And further, they never have the opportunity to have to have a time 3, time 4, time 5 inline continuance before there's a perturbance that gets them offline. Because in their cases, they're rotating dipoles right off the bat. And so then their time 3s are not going to be, you know, again, in line. In fact, they're not going to be in line for a second repulsion event. So as they move further away, the random walk probabilities for repulsive action will be less. So that on average, I suspect that we will see at high speed, all of the averages will come out to show us that particles statistically are going to attract toward these gravitational bodies, and statistically we will hardly ever observe them repel. But we need really big numbers in order to make this all statistical, because what I'm saying is statistical. I'm saying the statistical probability, if you could even measure at Planck scale time resolution and Planck scale space resolution, that the statistical probability of you observing a random walk moving away, like moving in this direction, would be a lot lower than the statistical probability of seeing things move on this direction, because of the 2 things that I talked about here, where the 1 over r squared, the fact that once it gets on an inline relation, it'll have a sequence of high probability for multiple sequences of jumping into it deeper, and then having a higher probability to link up again with another close angle, another very acute angle difference. Okay, so you know, this is very unrehearsed and didn't make diagrams, and I would suspect that each and every one of you have a different percentage of comprehension of what you think I just said, from 90% to 50% or 30%, okay? But these are the ideas that I want you to understand, because you guys have to start becoming interested in one or more of them, and then taking those and becoming the chief of that idea and developing that little module of our video game. You know, it's kind of like we're game developers, and we're going to be starting to take various components of the overall game physics and prove or disprove them, or learn what can be done. Okay, so now we're going to talk about this thing that I've been talking about all day, which is the S-index. And we're going to talk about my idea for functions, and I'm going to relate that to why we need an algebra, what kind of algebra we need. Okay, so, all right, so we'll just use a two-body problem, a two-body relationship. And we have our intrinsic state variables as, allow me to use these labels from physics without fully meaning them. But you remember we have three. No, I'll just use R3. I'm going to use mirror A and B. Actually, I'm going to use 20 group right, left. I'm going to use helicity right, left. And then we've got a dipole. That is a pole with a difference between the two sides. And so then our relational state variables.
Well, I'm a little unsure on the dipole. What's the difference between a dipole and a helicity right-left? You've been describing dipole like in terms of helicity right-left.
Right.
I thought.
Yeah. So the dipole is the one from in the first hour this morning, where I said this one is the most blurry one for me, because I said if I had a helix and I held it up to David, no matter which way I turn it, it's the same to him. There is no difference between the two sides of a helix, so a helix is not a dipole. And I was saying that my expectation of this complicated ruled surface that I believe relates to higher dimensional numbers, it is not just a helix. It is this complicated field.
It has a direction when you add the direction.
Right. So a helix doesn't have a direction on it, it has a helicity. So this thing, because it's moving in a direction, there's a distinct difference of symmetry breaking between this side of the helix and this side of the helix. And so there may be something very different about this part of the field and this part of the field. And I wanted to say it is the most blurry thing of any idea that I have today. And I had mentioned, I don't think we're going to be able to speculate and talk much about it as far as disagreeing or agreeing. I think we're just going to have to get to the stage where we can simulate this empire wave, understand a lot more about its structure and its topology, its ruled surface, everything we can possibly understand about it mathematically, and then understand S indices and two particle interactions better, right? And let the proof just come out from the simulation. But for right now, just to get to the S index and the function concept and the unitary evolution concept, just taking a fast statement of RSVs and ISVs. So d over t, that is its pitch value, it's another one, and then we have the cylindrical radius. So cylinder radius. So we have a bunch of these intrinsic state variables, and each of these leads to a relational state variable, such as, and we also have direction. So the direction is not an angle other than being an angle in the symmetry of the QSN. So it is an angle relative to the coordinates, if you will, of the QSN. But if I had two of these dipoles, right, in a relational state variable, right, now I have a theta, okay? So this relational state variable between two of the quasi-particles relating to their direction forms a theta, and then we've got a position as well, and the position of one in the coordinate space relative to another one in the coordinate space forms a distance between the two d, and so on, and you can figure out the others. But every one of them in the relational state variable column has a different number, which is kind of derivative of these numbers in terms of relationships with a set of these numbers, right? So like with the helicity, you can have a relationship left-left, right-left, and right-right. Okay, so we want to say we've got this empire wave here and this empire wave here, and they have any sort of combination of these different intrinsic state variables, which leads to all of the relative possible relational state variables that they have. This is a time one initial condition assumption that we have to plug in order to start our build out of an S index. So, so now we say, assuming these plugged starting condition relational state variables, we can then ask, all right, I want to go through the whole list. You know, I have a discrete set of d over t values, not an infinite set. I have a discrete set of directions, right, not infinite. So I've got this finite set of possible relationships that they can have. And my S index begins with one column, right, which is going to be my time to probabilities for measurement of the evolution of this two-body system, where every relationship has an optimal saving section. So if I place their dipoles like this, and I set the d over t's to whatever I set them, I set all the intrinsic variables, I set it, then I can say, now, solve for me the shape of the optimal saving section, which is a quantity of center emperor positions located at specific coordinates in our coordinate space, in our Dirichlet coordinate space. It's a shape, and that's the optimal saving section, and the shape is equal to also a number. That is, how many center emperor positions did it take you to describe that relationship? And again, it's not frozen. This is a time domain relationship. So we can say this is one full cycle. Maybe we call it 5 frames. And this is one full cycle. So it's this finite number of frames that acts as an animation to create the evolution, since our particles can only exist over time.
Is the dipole direction affect the savings between these two objects?
Does the direction between the two affect the savings?
Yeah, the dipole there, if I consider there is a dipole among the helix, a specific direction. If I reverse it,
yeah,
or if I change it, does it affect?
Yes, it does. Yes, that's my story. Yes, definitely. So basically, I run through all of the ways that I can manipulate my intrinsic state variables for a time 2 random walk of let's say it's going to be 5-step animation. So I've got a clock cycle on this one, and one pattern allows this one to kind of change directions. One pattern allows it to change d over t, right? One pattern allows it to flip its spin state, and on and on and on, right? You've got a heck of a lot of combinatorics, but they're countable. And you just start doing it by brute force. Not that we're going to be doing this by brute force, but we're going to do it conceptually here. So we do it by brute force, and we put an S value, In other words, this box represents an animation of evolution of this two-body problem. And the box has a number in it, which is the number that is the optimal saving section for that plugged relationship. So you get a number, x. Okay? Then we say we're going to go down the list. We're going to do the next one. So now let's do another one. This rotates, right? The dipole rotation. Any other change of your intrinsic state variables, which changes your relational state variables, wherein the relational state variables define what is going to be your optimal saving section. And most optimal saving sections for the different RSVs that are possible are different numbers. Okay, so I don't know how I should symbolize this, if I should do it with just S1, S2, S3. Okay, the point is we've got all these different numbers. Some numbers can be the same, by the way. Okay, but it's a large set of numbers, and then we say, all right, well, I guess that was time 2. That was hard. And we do the same thing at time 3. Now, obviously, time 3 relates very deeply to the integrated sum over histories that has to occur by integrating in what was probabilistically weighted for time 2. So you build out a table for as far as you want to go. And don't make me draw this table out, but this is now a grid filled with a huge set of numbers. This is time, universal time, not clock time. And these are the different probabilities of random walks. Couple interesting points here is that if you take a column or a row, you have to ask yourself, for example, on a row, all right, so let's say that I'm going to order each column by magnitude. So I'll put the highest S savings at the top and the lowest at the bottom, just to organize my data that way. And I say, all right, so now if I go across the time domain evolution of this thing and I say, oh, okay, so this is the highest probability evolution over 20 milliseconds or whatever, however far you've gone out. So you have to ask yourself, is this series of numbers orderly or is it chaotic? And if it's orderly, is it periodic order or aperiodic order? Because there's only 3 possibilities. It could be blends of those 3 things. But you can only have things that are orderly or disorderly. And in the category of orderly, you can only have aperiodic order and periodic order. And then there's subcategories you can talk about. But those are the meta-categories, the 3 meta-categories. So it's probably not going to be periodic, that is, the magnitudes of the values in this most highly probable evolution. So I say that's probably not going to be the case. Okay, what about disorderly? I mean, just purely random, like just nothing, like something a random number generator would generate. And I would say, hell no. I will put my $50 on the table and say that later this year we will find out there's just no, that's not going to be what comes out in the simulation. Why? Because this whole thing is based on order. The whole thing boils down to higher dimensional and time domain dimensional extensions of the Fibonacci matching rules. And that is an orderly code. The S values on these Fibonacci sequences, okay, are orderly. They have algorithms that describe their order. So I say that this series of numbers is an orderly series. And because I conjecture it's an orderly series, I conjecture that there is an algorithm or a function and or a function which describes that order, and whatever this algorithm or function is, it's going to have something to do with either Fibonacci numbers or the power series of the golden ratio, right? It's easy for me to conjecture that once I've conjectured that I think that there's order and I think that there's an algorithm that describes the order. Okay, so hopefully you really understand we can't do this. We can't build out S indices. The combinations, I mean, just my God, think about the optimal saving section for a 10-body problem. Oh my God, we can't do that. So we're going to have to understand what the order is that I speculate in these series of numbers, because this is our unitary evolution. And so with the quadratic function, that is a iterative function that if you carried out the infinity of iterations of the function that describes the Mandelbrot set, then you would have the Mandelbrot set. And if you don't carry out the infinity of iterations, well, then you have no Mandelbrot set, but at least you've got a compact function in an algebraic expression. So trivially, my point is that a function is not the output of a function. The Mandelbrot set function is not the Mandelbrot set. And similarly, if there is a function that describes the order of this series, then it is the function which must be selected by the universe, not building out or computing all of the substance that would come out from the computations of the function. Now, that won't do any good if when we do a measurement with our random number generator, we actually need to have access to this one and only column. That is, we're going to have the random number generator at time n make a weighted statistical random probability choice of one of these values for a random walk based on the magnitude of the S values. So the thing is can the computer, can our math, will our formalism allow us to get to this column? In other words, we're not going to tell the random number generator, this is time 50. We're not going to tell the random number generator to select a value from the column at time 49 or time 48 and so on. We're only going to do it when we program it to be done. Just like you only measure when you choose to measure. And the Copenhagen interpretation says until you measure, okay, the unitary evolution ensues, deterministic and unimpeded, with a function that was defined by the last measurement that was done on the system. And only when you do the measurement in the Copenhagen interpretation do you replace the first function with a new function, and you replace the old unitary evolution with a new unitary evolution. But for computational simulation-based physics, we actually have to think about the universe computing this stuff. And so do we want the universe greedy for economy? Do we want to expect that it's going to want to calculate this massively complex S-index table? So the only hope that we have, since it needs to dial in at will, that is when you choose to measure, then the universe is going to need to access that column in order to lens down the choices to either 1 square, if your measurement resolution is at 1 square, or if that means you have a Planck scale, Planck time and volume measurement resolution. If you don't have a Planck volume measurement resolution and you're at electron microscope level, near angstrom scale, which is 10 to the 23 orders of magnitude above the Planck scale, then you will lens down this S-index to a shorter or more compactified set of squares, which is equivalent to either a vibrating projection window in E8 or a mathematical superposition of various positions. So in the first case, before the measurement, the entire discrete probability space of the entire column would be a superposition of the shift vector window that covers all possible shifts. When you do the measurement, depending on your resolution, you compactify down that superposition set, or lens down to a smaller set of boxes. Now, physically, the laws of this game and the laws of physics, as I understand, allow, in principle, a Planck scale, time and space measurement. Don't know what kind of technology would do that, but in principle, that would be the limit. So in principle, one could mathematically collapse one of these S-index columns down to a single square. But in general, nowadays at least, it's depending on your measurement resolution. Okay, so back to the function idea. So I don't want to do this here at QGR. I don't have a supercomputer like Amazon, and they don't have a computer that can do this. There doesn't exist a computer that could build out the S-index for a 10-body problem like we have, I don't think. And 10-body problems aren't even good for interesting physics. We want to get to the point, how do we get to the point where we can simulate, a DNA molecule or H2O molecule, something really complicated? Okay, so with the Binet formula, the Binet formula is interesting. So we have knowledge of many series of numbers. Some of the series of numbers, we have algorithms that can allow us to dial in to a step in the series without using an additive function or some other function like the Riemann zeta function to sort of effectively count our way there, right? Like with prime numbers, if I say, hey, get me to the 10 to the 20th prime, then you could kind of count your way there. Or with the Riemann zeta function, that's a series of numbers. You have to count your way there. But there are other series of numbers that you don't have to count your way there. You can dial into the nth value. And so one of those series of numbers is the Fibonacci series, right? So the Fibonacci series is really cool in that it allows you to pick any Fibonacci number. So I can go to Fib 500. Okay, so that would take me a long time to do it with the computers we have here. But the Binet formula would allow me to dial directly in with right into the nth Fibonacci number without having any knowledge of what the earlier Fibonacci numbers are. And that is encouraging because this S-index might have something to do with Fibonacci numbers. What are the S values? Well, they're nothing to do with the golden ratio, right? They're integers. So I would not be surprised if the integer values of the S-index have something to do with Fibonacci or Lucas numbers, or some complicated, algorithm that uses them as a coefficient, right? So that's promising, because what if we could dial in to this time 50, where we want our computer to lens down and use the random, process with the weightings to make a selection, a single square selection or a lensed probability selection. That would be a blessing, because then we can set our initial condition in the game. We just set it, force it, plug it. Then we know that, and then we have a function. We have some kind of magic function or algorithm, and that object is nothing other than defined by the initial conditions and this principle of efficient language that's going to that's going to rank each random walk with a different S value. this simple principle based on empires and how you get overlaps and exploit the savings in different types of RSVs, different relationships. So I think Ray is closest to advanced thinking on this idea, you know? So maybe this will be something Ray will kind of advance on over the next periods of time. But long story short is whether Ray finds it or any of us find it, we have to find it. Because otherwise, we've just got a really cool game of life that has physical things that are physically reminiscent at simple levels. But I really want to just compute these. I just want to do these collapses very infrequently because measurements don't happen very often. If reality has a CPU speed at the Planck time, 10 to the 44 events per second, then measurements, right, are not happening with a large ratio of those frames.